Hello? Hello?
Good evening, sir. Good evening,
Yeah.
sir.
Good evening, sir.
So I think we need to wait a while. One student will join. Or what do you think? Let's just wait maximum of 4 minutes so that we can start at 5:05, right?
Yes, sir.
All right.
Please, we should not-
Deborah Uteneko, mute yourself. Deborah, can you hear me? Mute yourself. Mute yourself. Everyone is in this class to learn. I need to listen to you speak.
The class governors should indicate I want to make you co-host, so I can have 5 co-hosts. All right, just hold on. So once you have been made co-host, you can just lower your hands. Adewumi, you can lower your hands now. Bolaji, you can lower your hands. You are now a co-host. So we'll be managing the class together. If there's any of you that is flouting the rules of being muted, you just assist to mute that individual. Please do not eject anybody. Okay, hello everyone. I think we need to start. Others will join us if they want. Otherwise, you can make this recording available to them. So my name is Adeleke from the Department of Actuarial Science and Insurance. I will be assisting in teaching Markov chains as part of the topics in LVA 410. So earlier on, I've made these materials available, and I've also prepared some other videos and so on that I feel will be very helpful for you guys. So please take advantage of it and see how you can maximize your knowledge. So while I'm teaching, if you have any concept that you want me to re-explain, you can just indicate by using the hand raise icon. I will attend to you. Please feel free to express your mind. You are free to complain. You are free to also contribute, and you can also make suggestions. So I will be going through this outline. I'll describe what a stochastic process is, so that you can see the link, okay? What stochastic processes and how important they are, and then what do we mean by the Markov properties, and then we'll describe the Markov models, and then I'll go to the Markov chains, discuss the properties of Markov chains, and then show examples. In fact, I will demonstrate using the Excel how to derive what I call the transition matrix from the first principle. This is an area that is very, very applicable, but it is hardly used because of the seamless, people see it as if it is difficult, but it is not difficult at all. It is very, very useful. So I'll start with stochastic process. I will de-emphasize the mathematics, so you should pay attention more to the explanation and the concept. Any random phenomenon, a random variable, any activities that involved the use, that involves taking into account time of events, can be stochastic in nature. We define stochastic process as a collection of time-dependent random variables. Okay, so anything that will take into account the time at which an incident occur, the time at which readings are made, the times at which processes change, a stochastic process. So simply put, we say a stochastic process is a collection of time-dependent random variables. Now, those random variables or those activities will be in a particular location, will be in a particular condition, will be in a particular, in quote, state at any given time, or will assume a value, okay, at any given time. So those values that the random variable takes is called, the values are called states. States. So if I have a random variable that measures the health condition of an individual, and I'm using maybe a two-state model, two-state scenario, an individual being alive or an individual being dead. So in that case, my random variable can be in the state of healthy alive or being dead. So if I also run discount levels for my customers and I place them on 20% discount, 30% discount, 40% discount. So if I have 3 possible discount level for my customers, then those discount level are the states. So someone can be on 20%, 30%, or 40%. And it could also be values. I'm monitoring stocks and I'm interested in the closing prices, So which means that my random variable here is the closing prices. So if the particular stock would take a value at the end of the activity on the stock exchange. So the stock can take the value 120 naira.25. That is the state at that time. So the state that the random variable, the value or the position that the random variable takes is called the state as far as this stochastic process is concerned. So if I put all the possible states together, I have what I call the state space, just as you have the sample space. You know, sample space is the set of all possible outcomes of a random experiment. So I could also have that in my stochastic process that, look, what are the possible states that my process can be? If I put them together in a set, I have what we call the state space. Now, the time of the realization, okay, all the possible time that those random variable assume those states, if I put them together in a set, I have what I call the time set. So the combination of the state and the time will determine the type of stochastic process that you are dealing with. Remember, we want to analyze data that are time-based, and that time is very important to you. In addition to the values or the states or the realization of those random variables at those times. So how do we classify our stochastic process based on the time and the state? Remember how I defined the state? I said the realization, the position, the value of the random variable is your state. And then the time that the random variable gets to that state, the time that it transited and assumed those values is your time. And then when you put all those possible times together, you have what we call the time set. Just have this at the back of your mind so that when I'm using the word state and I'm using time, so you should understand. So our time can be discretized, but naturally we know that time is continuous. Why is it continuous? Time is measured. Any value that is as a result of measurement is continuous. But those values that are as a result of counting, they are discrete. So you should have this at the back of our mind. So this is part of the definition that I was discussing earlier. So now let's look at the possible states that our random variable, our stochastic process can be. The 5 possible types of stochastic process, or the 5 possible classes of our stochastic process. So if you look at the table above, you have 4 different quadrants there. The 5th one is hidden. and I'll explain later. Now, in the first quadrant, you can have a stochastic process that the time is discrete and the state is discrete. So what it means is that the stochastic process will assume a definite position and at a definite time. So you can have the time as time 1, time 2, time 3, just as you have in the case of day 1, day 2, day 3, or week 1, week 2, week 3, and so on. You have discretized the time. And then the state. So you could have, by day 1, this customer is enjoying 10% discount. By day 2, this customer is enjoying 40% discount. So the discount level is also discretized. It is definite. So it is not continuous. So in that case, you describe your stochastic process as time, a discrete time, and discrete state process. So, for example, for those in insurance, in the motor insurance policy, we have this no claims discount that is practiced by insurance company to encourage good behavior, in quote. So as much as possible, the insurer don't want the policyholder to make claim. So they can introduce discount on the premium for the policyholder if no claims are made. So you could have it that by the time you are buying the policy for the first time, you enjoy no discount because you don't have any historical record with them. So you can start at 0% discount. At the end of that policy year, your position is reassessed, and then they look at your profile as to whether you have made claims or not. So if you don't make claim, yeah, you're a good customer, so they give you discount on your premium. So you can enjoy maybe 20% discount at the end of that policy year. So in the new year, you pay a premium that is less. And then at the end of that particular year, that's the second year, you will also be assessed. And then your discount level will be determined. So you can have maybe up to 40% discount. And then you could also move down, move backward. So my co-hosts should do their work. Mm-hmm. So you could also move downward too. In case you made a claim, the policy could say, go back to discount level 0 and start all over again. So in that case, you have a stochastic process that is discrete in terms of the timing and also discrete in terms of the state. That's one category. You could also have a stochastic process that the state is discrete. That is the position that you will be at any time, the value that you will take at any time is discrete. But the time set is continuous. Now let's look at the HMO, scenario. The HMO would register the enrollee and then provide healthcare services. They are not the ones that will provide anyway. There are providers, the hospitals that the enrollee will go to when they need healthcare service. So the HMO will pay on their behalf for a fee that they have made at the time of effecting the contract. So to the HMO, they will be interested in the number of people that will be healthy at any point in time, number that you expect to be sick, number that you expect to be maybe critically ill, terminally ill, or dead. So if I run a 4-state model such that the states are being healthy, being sick, being critically ill, or dead. So the states are definite. But the time of transition, of course, will be continuous. Anybody can fall sick at any time. So you can't impose time on the time on an individual in terms of when that individual should fall sick, when that individual should be critically ill, or when that individual should transit into the state of being dead. So in that case, the transition time is continuous, but the state is discrete. So if you have that kind of scenario, you are dealing with a stochastic process that the time set is continuous, but the state space is discrete. Now let's move to the next quadrant here, okay, where the state space is continuous, but the time set is discrete. So I want you to look at the weather report. Now, let us assume that you are interested in the daily weather summary, like the daily temperature, maybe average temperature on a daily basis, average daily rainfall, and so on. So in that case, average is a measurement, it's not counted. But you have discretized the time. You have said daily. But the average temperature, remember, it is measured in maybe degree Fahrenheit or degree Celsius. So it's a measurement, and whatever you arrive at is continuous. So it could also be daily returns from maybe a security that is traded on the floor of the stock exchange. So because you have discretized the time, we have made it daily, but the state is continuous. Remember, it's as a result of measurement. So if you have that kind of process, you are dealing with a stochastic process that is continuous in terms of the state, but the time set is discrete. And the fourth one, the state is discrete, the state is continuous, and the time is also continuous. So I know many of us have one coin or the other. You have some crypto coin that you trade. So you do the trading on different platforms. You will notice that whenever you monitor your crypto price on your platform, you will observe that the figures are changing continuously in terms of maybe the price or the volume, whatever. You will also notice that the graph, that you can use as an indicator to trace whether your stock is rising or falling, is also changing continuously. In fact, per nanoseconds, the values are changing. So, and of course, the time in this case is continuous. The state too, which is the price of the stock, is also continuous. So if you have that kind of process, like the crypto price monitoring activity, it's a stochastic process of continuous state and continuous time. And the fifth one, that is hidden, is not visible on the table. But the fifth one is actually a mixed process. It's a stochastic process. At the time, is a combination of discrete and continuous. The state is also a combination of discrete and continuous. So these are the types, these are the five classes of stochastic process that we can have. So remember, I said you are dealing with a process that time is of essence. And that process can be described as a stochastic process. I define the stochastic process as a collection of time-dependent random variables. I mean, it's a set, okay, that has all the random variables, x1, x2, x3, up to xn, if the observation stops at time n. And then the values that each of the random variable takes are also being observed. So I said those possible values, the possible realization, are called the states of that random process. And the time that the random variable take those values can be discrete or continuous. The collection of all those states, all those time, is called the time set. And that our stochastic process can be easily classified depending on the time set and the state space. So please feel free, you can ask questions anytime. And you can let me know if there's any concept that is not well explained. So on the screen is just an illustration of some of these concepts that I've explained. So in this case, we have a motor insurance company that review the status of its customers yearly. And there are three levels of discounts that the customer can enjoy: 0%, 25%, and 40%. So those are the states. If you collect them together, you have what we call the state space. But because the timing of the classification of the customer is yearly, so the time set would be a whole number, and of course that makes it discrete. So that's an example of a discrete state space with discrete time changes. So I also gave an illustration on the three-state model for healthy, sick, or dead for health insurance process. So the time set, of course, can be considered to be discrete if time has been discretized. But we all know that in the real sense of it, time to fall sick is continuous. I'm sure you have heard stories of someone that is being very, very healthy, falling sick just immediately, after you have observed that person to be healthy. Well, and we have also seen someone that transited to the state of being dead, just after someone have seen him and he says, oh, this person is hale and healthy. So time of transition can be continuous. So you have all of those. So that takes us to an important term, which is called the Markov property. Now, there are some processes that their next state, assuming their current state is being measured, their current state is being observed, and their next state depends on the current state only, irrespective of the historical past. If you have that kind of process, then you say that you have a Markov process. The Markov process must be a stochastic process. But in addition to it being stochastic, it should not keep memory. It doesn't keep memory at all. So if you have that kind of process, then you say you are dealing with a Markov property. You can look, let me take you back to the insurance example. The policyholder is being examined at the end of the policy year, and then will be given discount based on the current year. So I activated the policy between January 1 and December 31st. So my policy will be active from January 1 and closed by December 31st. By December 31st, I needed to renew against January 1. So as part of the regulation. So how much should I pay in terms of the premium by January 1? The insurance company can give me discount if I have not made claim during the current policy year. Current is the key word. It is not based on your historical past. The fact that I've been a good driver for the past 15 years, and then I'm in the 15th year and I want to renew my policy for my 16th year. And during the 15th year, I'd made at least one claim. The insurance company wouldn't say, oh, this man has been good for the past 15 years. Let's give him discount. No. So what they will do is to penalize that customer to a lower level discount, or keep him at 0% discount. So that kind of process is memoryless. That process doesn't keep memory at all. It doesn't keep historical antecedent. That what is concerned with is your current status. The current status will now be used to determine the next state. So if you have that kind of process, you will say that that process has the Markov property. Okay, Markov property. So I want you to consider this time. So the time that any process stays on a particular state is called the sojourn time. Sojourn time. So if for example, I'm a very bad driver and I'm not enjoying any discount level because for about 3 years, for instance. So before I could gain a discount, to enjoy maybe 20%. So that means my sojourn time is 3. And it's because I've been making claim consistently for 3 years. So the time that a process stays on a particular state is called the sojourn time. Now, moving from one state to another, as far as stochastic process is concerned, is called transition. Transition. So we will avoid the use of moving from this point onward. We'll be making use of the word transit. Transit. So a process changing from one state to another is called transition. Transition. So the transition probability would be the chance that that process will move from one state to another. My co-host, you should do your work. You should do your work. Help me mute some of our colleagues that are always forgetting that muting ourselves is part of the ethics of online teaching. So now I want to share my Excel sheet. So I will create a scenario, and then from that scenario, we will all generate the transition probability together. So once we have generated this transition probability, then we'll go back to our PowerPoint. So I will reshare my screen now so as to take advantage of that. So I'll share the whole screen rather than just sharing that document. So I want you to confirm that you can see my Excel. You can unmute now and confirm. Can you see my Excel sheet?
Yes, sir.
We can see.
Yes, sir.
Yes, sir. We can see.
All right. So I want to make it bolder. So now let us create scenarios so that we will all compute transition probabilities. Let's create scenarios. So let us assume that you are a big distributor. You distribute cement for Dangote's cement industries, and there are 5. Okay, let's make it 3. 5 discount level that you can enjoy, and they have advertised their criteria. If you can sell 100 tons in a month, you will enjoy 20% discount. If you can sell 200 tons, you enjoy 30% discount. Otherwise, you enjoy 0% discount. So that means there are 3 different discount levels. There are 3 different states. So let's make it state 1, 0%, state 2, 20%, state 3, 30%. So that means I'll be making use of the label 1, 2, 3 to denote the state so that it's easier for us to track. Now, you are just joining them and then they place you on state 1. After the 1 year, you are so good. Okay, let's assume that, monthly. After 1 month, you are a very good customer. You have moved to state 2. You remain at this state 2 for some time, and then suddenly you moved up again to state 3 and remain there. But you started having financial difficulty, and then you moved back to state 1. And then from state 1, let me make it smaller so that I can take more. So from state 1, you move to, okay, I don't want it to be, okay, so let's assume that the second line is a continuation. Okay, I don't want to start scrolling from left to right. So let's make sure that everything is on one page. So from state 1, you move to state 2 and remain there for a while. And then your financial status improves. You move to state 3 and remain there. And then again, the cycle of financial difficulty came in. You move to state 1, move back to state 2, move to state 1, move back to state 2, to 2 to 3, and then 3 back to 1. So let's assume that you have been observed for how many months now? 22 months. So 22 months. So the question now is, now that is currently in state 1, what is the probability that this customer will move to state 2 in the next financial year? That's a challenge. So if we don't understand this pattern, it will be difficult, for you to start making that projection. And I'm sure you also know that I can use that probability to estimate how many of my customer will be enjoying state 1, how many will be enjoying state 2, how many will be enjoying state 3. I can easily do that if I know the probability that any of the customer will be in state 1, will be in state 2, will be in state 3. So if I have 1 million customers, I'll just multiply the probabilities by 1 million, and then I will have an idea of how many to expect in state 1, how many to expect in state 2 and state 3. So then let's do this together. So we shall capture this information in a table. Okay, so the table will actually be a contingency table where I have my from, the state where you are currently are. So I call this current state. Okay, so that will be this. Then I'm moving to the next state. All right, so let's call this the next state. That will be next state. So I can do this and then make it center. So let's call it next. So remember, the current state can be state 1, 2, 3. In fact, if I like, I can put the discount level, at the in bracket, and then the next state can be this state 1, 2, and 3. Okay, so what we want to do now is to start counting. How many times have you observed a process or a customer that is currently in state 1 remaining in state 1? How many? That is in 1 now, and then the next state it remains in 1. So you try and count how many times have you observed the pair of 1 and 1 together. So if you look at this, you will notice that you have 1s together. Can you see it? So which means that at time I is in 1, followed by 1 in state J. So, sorry, at time J. So that's 1. You have observed it once. And then from J to K is another time that you have observed the customer being in state 1, and then it remains in state 1 at the end of the next month. So it is 2 times that you have observed it. And then you check through all the data, there are no other times. So this is 2. You are counting now. 2. I think I need to, so that Oliver, go ahead.
Okay, good evening, sir. Please, can you come back explaining how you got the 2?
Okay, I'll do that now. Let me do the proper labeling of my current state and the next state so that there won't be any confusion. Okay, so let me explain how I got the 2. Now, you are currently in state 1. This is the current state 1. And then you are looking at the number of times that you observed the process to transit back to state 1. How many times did you observe it during the the tracking period. So you will notice that here is starting at state 1, but at the next period it was in state 2. So this condition doesn't apply. But you are looking at the scenario where you started from 1, and then the next one you are also in 1. So you are looking at how many times did you observe that kind of a scenario. So you can see that from I to J, it's moving from 1 to 1. That's one scenario. And from J to K, the K, I'm using the numbers at the top of the column, to represent my time. So from J to K, you can see that it's also moving from 1, and then at K, it returns back to 1. What it means here is that the customer was enjoying no discount. It was on 0% discount. And then in the next period, it still remained at that 0% discount. That's one time that you have observed it. And then even from J to K too, you also observed it. It was in 0% discount at time J. And then in time K, is still at 1. It's still at state 1, which is 0%. That means there are 2 times that you observed it. I hope it's clear, Oliver. So the next one is moving from 0% to 10%, moving from 1 to 2. How many times did you see 1 and 2 together in pairs? Because 1 and 2 simply means you are currently in 1, and the next period you will be in 2. This is the first scenario. You can see it because at time A, it was in 1, and at time B, it ended up in 2. That is 1 moving to 2. That's 1. You can also see it in F to G. It was in state 1 at time F, and then at time G, it was in state 2. That's also another one. That makes it 2. Then you also see it H to I, moving from 1 to 2. That means there are 3 of them, 3 different times that you have observed it. Okay? Now let's move to 1 to 3 now. 1 to 3. How many times did you observe it? I want you guys to participate now. 1 to 3. There's no scenario that you get 1 to 3. None. So it is 0. Okay? So we don't have a customer that is so excellent in performance that if he's currently not enjoying any discount, that he'll be enjoying up to 30% discount in the next period. Eunice.
Sir.
Yes, go
sir,
ahead.
The number 2 is the number 2 on the vertical line is continuation of where K stopped.
Yes. Oh,
so
yes.
There are 4 scenarios there then.
Yes. So let's recount. 1 to 2. This is 1, right? So that means this and that will also give us another one from K back to A. That makes it 2. And then this is 3. And then 4. So there are 4 different time. Someone else is raising up his hand. Is it Daniel? Go ahead, ask your question. All right. So now let's move to from 2 to 1. Okay. He's enjoying 10% discount, but in the next period, he's now enjoying, that means there was a downgrade. He's now enjoying no discount. So you notice that it's here that you can see it. 2 to 1. This is the only scenario. 2 to 1. That means it's one once that I've observed it. Then 2 to 2. That means he was enjoying 10%, and then he remains at 10. Okay, this is the scenario. You can see it. 1, 2, 3, and 4. 4. Okay. Then 2 to 3. Let's look at it. 2 to 3. This is 1. This is another one. Making 2. There's no other one. Twice. 3 to 1.
So there's one at the I to J, 2 to 3.
It's 3.
Okay, let's look at it. 2 to 3. This is 1, right? And okay, it's another one. 2. Yes. Thank you. 2. And there is another one. 3. So that means it's 3. So someone else is raising up his hand. Okay, so let's look at 3 to 1. 3 to 1. We have this 1. We have this 2. And then we have that 3. 3 to 1, there are 3 possible times that I've observed. Then 3 to 2. Let's look at it. 3 to 2. 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 None. Do you agree? That it is none. Then 3 back to 3. This is 1. This is 2. This is 3. This is 4. 4. So I want you guys to have a look at it for the next 30 seconds. And then we'll take it up from there.
Hello, sir.
Okay, so let's continue. So for us to calculate the probability, we'll find the total row-wise. Row-wise. So let's find the total row-wise. So we just add up. We add up row-wise, and then we get our total. Oliver, go ahead.
Okay, sir. I observed that you didn't count the under the H column, the 3 to 1. You didn't count it.
Okay, so okay, let's do it again. 3 to 1. Oh, yeah, let's start from the beginning. There's none here, none here. So you have this 1, 3 to 1. Then let's move. There's none again. So let's go back to the next line. 2 is another 3 to 1. And then 3 to 1, that makes it 3. So 3 to 1 is 3. That's why we have here. But you are not moving down because this is a continuation. Okay, from here, it's a continuation. It was supposed to be from L and then downward that way. But because I don't want to be scrolling, moving, scrolling left and scrolling right. So I want everything to show on the page.
Okay, I understand now.
So now what we have here are the observed frequency. Okay, Rachel.
Yes, sir. Sorry, sir. Please, can we check 1 to 2 again?
Okay, 1 to 2. Okay, let's look at this. 1 to 2, 1. We move on, we move on, we move on, we move on. But there's 1 here, followed by a 2 here. Can you see it? There's 1 at K, followed by a 2.
Okay, sir.
And that makes it 2. And then there's 1 here, 3. And there's another 1 here, 4. So that's why it is 4.
All right. Thanks, sir.
All right. So what we have here are the observed. Now let's calculate the probability. So the probability will be calculated by dividing now. We will divide each of the cell by the addition on that row. So we will divide 2 divided by 6. This 6, the total there. So that gives you the probability. Okay, and you divide for each of the cells. So you can use your calculator to divide. And sorry.
Sorry, sir. I couldn't hear what you said. So what you say we're dividing by again?
By what?
I think the network was breaking. You said we're dividing by what?
Okay, by the total for each row. For each row, by the total. So, for example, you use 6 to divide 2, use 6 to divide 4, use 6 to divide 0. Okay? So the next one is 8. You use 8 to divide 1, use 8 to divide 4, use 8 to divide 3. Okay? So that is what we are doing. Now, what we have in this cell, let me paint it yellow. This is what is called transition probabilities. Transition probabilities. So this is the probability that a process that is currently, or a customer that is currently enjoying no discount will remain at that state, will still not be enjoying discount in the next month or 1 month after. That means there is a 33% chance that a customer that is not currently enjoying any discount will not enjoy discount in the next month. This 0.67 is the probability. That means there's 67% chance that a customer that is currently enjoying no discount will be enjoying 10% discount after 1 month, and so on. So this is what we call the transition probability. So I'll go back now to the PowerPoint. I just want you to visualize, all the terms that are being used. So can you see my screen? Can you see
Yes, sir. Excuse me, sir. Can you please go back?
Yes, sir.
Sir, can you please go back? Let's just take a screenshot of that.
Okay. I will share this Excel after the class. Okay. You want me to re-explain?
No, sir.
Okay, don't worry. Immediately after the class, I will share this Excel so that you can use it. Adeloye.
Yes, sir. And sir, I have a question, sir.
Go ahead.
Okay, so sir, why did we add it row by row and not like column by column?
Oh, okay. You know what matters now is your current position. This is you currently. So the next is for the future. This is the one that you can own. This is a state that is sure. Do you get it? And the current state is arranged row-wise. So that is what is important. And that's why it is the one that we added. We are not moving from the next stage, which is tomorrow, moving back to today. It is impossible. You can only move from this current state to the next state. You can't move from this current state to the state that is previous, because you had left that previous state. So that's why it is the current state that matters. It is the current state that we add. I hope it's understood.
Yes, sir. Thank you, sir.
All right. So we will now go back to our PowerPoint and then continue with the story. You can remember how we started the story. So I said there are times that we are dealing with data that are time-based. All along, calculating taking decision via some criteria, time have not been factored in. Okay, the only time that you put in, that you consider the time, is when you are doing time series. Okay, and then maybe you do exponential smoothing, you do moving average, and so on. But you will agree with me that time series actually falls in one of the quadrants where the time have been discretized, but your state is continuous. That's where it falls. But this is the first time that you are recognizing that problem as a stochastic problem. That look, whenever you are considering a scenario that time is of essence and needed to put time into consideration, you are actually in the realm of stochastic process. So I define a stochastic process as a collection of time of random variables that are time-based. And that those random variables at different times, they take their value. They also assume position. They take different realizations. Those values, those realizations, those positions, they are known as the state of the process, the state. But the time that they get there, the time can be discrete and the time can be continuous. When you put all the possible states together, that is the possible time, the possible values, the possible realizations, if you put them together in a set, remember you were told in your SS1 that a set is a collection of well-defined objects. So when you put them together in a set, you have what we call the state space. That is the possible values, the possible observation, the possible realization that our process can take. Then the time too, when you put them together in a set, we have what we call this time set. Time set. Now, the combination of our possible time and our possible state will determine the type of stochastic process that you are dealing with. Because it is the type of stochastic process that will dictate how you will analyze that process. So if you don't understand the stochastic process that you are dealing with, then it's difficult for you to analyze. Our co-host should do the needful, please. So we can have a stochastic process that the time set is discrete and the state space is discrete. That's one type of stochastic process. And I've given you scenarios. You can also have a stochastic process that the time set is continuous, but the state space is discrete. It's another type of stochastic process. You also have a stochastic process that the state space is continuous while the time is discrete. And then you have a stochastic process where the time is continuous, the state is also continuous. And then the fifth one that is hidden is the mixed stochastic process. Okay? Sometimes the value will be whole numbers, discrete. Suddenly it will just suddenly change and become decimal. That's mixed process. Okay? So and so on. So then I introduce a term that is Markov. So I said a stochastic process is Markovian if it doesn't keep memory. That is, the next stage that the process will be depends on the current state only. It doesn't put into consideration the historical past. And what we are interested in is actually how to compute probabilities of a process transiting from one state to another. If you can do that, then it's easy for me to make projection. So I have demonstrated how you can derive the transition probability from first principle. And that was why we use that Excel, okay, to monitor the classification of a particular Dangote cement supplier on a monthly basis. And we have identified 3 different states, 3 different discount levels that cement supplier can enjoy. Can enjoy 0%, can enjoy 10%, can enjoy 30%. So we derive the transition probability from first principle. So that's what we have done. And then we are moving forward. So the next now is for us to define what we call the Markov chain. Remember that the topic I'm supposed to teach you is actually Markov chain. But we needed to understand the concept of stochastic process, needed to understand the concept of Markov process for us to understand the Markov chain. So a Markov chain is actually defined as a stochastic process that has the Markov property and has discrete state space and discrete time set. I'll take it again. A Markov chain is a stochastic process that is Markovian in property, and the state is discrete, the time set is also discrete. That's what makes it a Markov chain. So Markov chain, 4 properties or 4 different terms. It has to be a stochastic process in the first place. It is Markovian. The state is discrete, the time set is discrete. Okay, so that is what we are dealing with. Of course, it was introduced by Andrei Markov, sometimes early 19th century, and it has been found useful in almost every field. So, if the time sets have been continuous, but the state is discrete, we will have called it a Markov chain. A Markov jump. But we're not interested, okay, in a Markov jump. But what we're interested in is Markov chain. So the transition probabilities. So remember, I have demonstrated how it is computed. So when you have a matrix that contains the probabilities of the process transiting from one state to another, we have what we call the transition matrix. A matrix is an arrangement of objects in rows and columns. So what you are arranging, if they represent probabilities, and those probabilities are not just any probabilities, they are probabilities of the process transiting from one state to another, then what you have is a transition matrix. And it has 2 major properties. Number 1, the cells are non-zero. All these probabilities, they are non-zero. And the addition of each row must be 1. Transition probability, transition matrix. There are 2 different things. The matrix is the arrangement of our probabilities in rows and columns. And the transition matrix has 2 properties. Each of the cells are non-negative. Each of the probabilities are non-negative. And 2, the addition of the probabilities for each row must be equal to 1. So if you have that, that's your transition matrix. And you can draw the graph of a transition matrix, which is called transition graph. It shows you how the process moves from one state to another. Now let's consider the graph that is before us. So let me interpret the matrix and then we look at the graph. Now, 0.65 here simply means the probability of the process transiting from 1 and then going back to 1. This is 0.65. 0.28 is the probability that the process that is currently in 1 will end up in 2 in the next process. Okay, that's 0.28. 0.07 is the probability that the process that is in 1 will move. I don't want to use the word move. Will transit to state 3 in the next time, 0.07. 0.15, this process moves, the process transits from state 2 to state 1 in the next period. 0.67, transit from 2 and back to 2. 0.18, transit from 2 to 3. 0.12, transit from 3 to 1. 0.32, transit from 3 to 2. 0.33, started at 3, transit back to 3. Now, let's look at the diagram. Look at the diagram. You can see that we use circles to represent the state. In some textbook, it is square that will be used. In other textbook, rectangle can be used. Now, I have 3 states. You can see 3 circles there. Circle 1, 2, and 3. And then they are properly labeled. 1, 2, 3. The arrows shows the transition, and the direction of the arrow shows where the state is currently is and where it is transiting to. Now look at 1. You see the arrow blue moving from 1 to 2. That is the probability of the process transiting from state 1 to state 2 is 0.28 on this diagram. And it's the same here on the matrix. So if you follow through, you will see that the diagram is actually produced using the matrix above. This diagram is called the transition graph. Transition graph. The matrix, arrangement of objects in rows and columns, is the transition matrix. This contains the probabilities of the process transiting from one state to another. Now let's look at this simple example. So the weather condition can be used and as an example. If you have 2 states model for the weather, either the weather is sunny or cloudy, and you know the probability of a cloudy day following a sunny day, or a sunny day following a cloudy day, or a cloudy day following a cloudy day, or a sunny day following a sunny day. So if you have that from your weather experience, if you know how many times that you have experienced such, then it's easy for you to compute the probability just the way I did, in our previous examples. Then you can easily get the transition matrix. You can see it. So in this case, it says 0.8, or there's 80% chance that a sunny day will follow a sunny day. A sunny day will succeed a sunny day. But the probability that a rainy day, a cloudy day, will come after the sunny day is 20%. While 60% is the probability that a cloudy day will be followed by a sunny day. And then there's 40% chance that a cloudy day will be followed by a cloudy day. So you can use this. So why is this stochastic? Why is it Markov? It is Markov because you are not concerned about 2 days ago. You are only concerned about the current. Today, is it cloudy or sunny? If it is cloudy, all right, then tomorrow, what follows? It is not what happened yesterday. You add it to today and then you project and start looking at tomorrow. No, you only look at 2 consecutive days and you're not keeping any memory. That's what makes it to be Markov. So our Markov can be regular Markov and it can be adsorbing. Regular Markov and it is adsorbing. So whenever you have the probability greater than 0, then you are dealing with a regular Markov chain. Otherwise, if you can have a state such that the probability of it remaining in that state and not moving out is 0, is 1, then you have an adsorbing state. Like in the case of being healthy and dead. So if we have 2 state model and one is being alive and the other one is being dead, so you will notice that the movement or the transition would definitely be a one-directional transition. One can only transit from being healthy to dead. You can't transit out of it. Once you move into it, it becomes an absorbing state, because the probability that you will transit back is absolutely 1, because you will remain there. Okay, so you don't transit out of it. So, so you can have that those two types of stochastic process. So how do you now use the probability? That's our concern. That is exactly where we are going. So now we'll go back to the Excel and apply it. How do we make use of the probability? We actually raise our P to power of n to compute our probability. So I can raise P to power of n. So n there is the number of steps or the number of future periods that I want to forecast. So if I want to forecast the probability that a customer that is currently enjoying 20% will remain at 20% in the next 2 years, I will raise my P to power of 2. Ola should become.
Sorry, sir, can you explain the regular and absorbing Markov chain again?
Okay, so I'll go back. So it says a Markov chain is a regular Markov chain if some powers of the transition matrix has only positive entries. That is, if we define our ij, I is the state, I and j, they are the states from state I to state j. Okay, then it is regular. If there is, so if there exists n such that the probability power I raised to power of n is greater than 0, what this is saying is, if you raise your power maybe to power of 2 and you check the cells, all the probability inside that matrix, if all of them are greater than 0, then you are dealing with a regular Markov chain. I'll take it again. You have a matrix, you have a transition matrix, and you raise it to power of 2, for instance. That means P times P. The probability that you arrive at, if all the cells, all the probability inside that matrix are greater than 0, none of them is 0, then you are dealing with a regular Markov chain. But if you compute and then you discover that one of the cells is absolutely 1, that is moving from a state and then returning back to that state, you have it as 1, such that moving from that state to other states is 0, then you are dealing with a Markov chain that is absorbing at least one of the states. It's a state that you will get into and you can move out. I hope you understand what I just explained. So now, let's see how we can raise these probabilities, and then we'll now use it in computing probabilities, and then we will take the long-run behavior of our probability, and that is what we call the limiting distribution. So I'll go back to my Excel. Now, this is my matrix. It is P, capital P. That is the transition matrix, and it shows the probability of a customer enjoying different levels of discount at different point in time. So he is currently 0%. The probability that he will be 1% is 33%, or 0.33. The probability that he will move to 10% is 0.67. However, as it is, it's not possible for the states to move from 1 to 30 because the probability is 0. Okay, that is, you move from 0% to 30%. It is 0 at this instance when P is raised to power of 1. Now let's raise P to power of 2. So I'll do it up to power of 5. So that means I will show you how to do matrix multiplication in Excel. So I will copy this and paste 5 times so that I don't have to 62, 63, 4, 5. So I can let me delete the cells so that I don't create confusion. I've not done anything. I only created this space so that we can use it for our computations. So I hope nobody is confused here. All right. So this is P squared. P to power of 2. I'll use carat to denote raised to power. This is P to power of 3. P to power of 3. I use carat. This is P to power of 4. P power of 4. I use carat. And then P to power of 5. I use P to power of 5. All right. So now let's raise the power. So this is a function. In algebra, we all know what raised to P times P square is. That's P times P. Okay, Oliver, do you understand? When you want to compute P squared or X squared, you multiply X by X. So it's the same concept here. To get P squared, you need to multiply the matrix by itself. So the function that is used in Excel is M mod, M matrix multiplication. So I will highlight where I want the result to be, and I'll type equal to. Okay, then I type M mod. This is M mod. I'll take it again. I have highlighted. Okay, in the first cell, automatically my cursor will be there. Just type equal to, and then you type M, another M. You will see that M mod will pop up. M mod simply means matrix multiplication. So I'll double click on it, and then I need 2 different matrices because remember it is P times P. Matrix 1 P times matrix 2 P. So the P is here. So I'm going to highlight array 1, the first matrix, comma, and then array 2, the second matrix. When I am done, I will click on control, leave my hand there, click on I'll click on shift, leave my hand there, click on control. Simultaneously, my fingers are on shift and control. Then I will type enter so that the cells will be populated. So what we have here is the probability after 2 years. Now let's do after 3 years. Again, how do you get P to power of 3? It is P times P to power of 2. P to power of 1 times P to power of 2. So again, I will highlight where I want my result to be. I will type equal to. Then I type my M, another M. The M mod will pop up. M mod stands for matrix multiplication. So I'll double click on it. Array 1 is the first matrix P. Remember P cube. I want P cube is P times P squared. So I will go and highlight my matrix 1, then comma, I'll put comma there. Then I highlight my matrix 2. And that's all. This time around, again, my 2 fingers, one on shift, one on control. And then I'll type, I'll click on enter, and then I have the result. So this is after 2 years, after 3 years. 4 years, P to power of 4. It could be P to power of 2 times p to the power of 2. So again, I can highlight. Okay. Again, I type equal to m mod. M mod, just type mm and then m mod with triple. Double click. So I will do p to the power of 2 times p to the power of 2. I could also do p times p to the power of 3. It will give you the same thing. So I'll do p to the power of 2, okay, comma, and then I'll do another p to the power of 2. And that's all. Then I will type my control and shift will be locked down simultaneously, and I'll type enter. And then I have my results. Okay. Then lastly, I'll do p to the power of 5. Again, I will highlight where I want my result to be. I type equal to m mod. When you type m mod will pop up. And then p to the power of 5 will be p to the power of 1 times p to the power of 4. It's also p to the power of 3 times p to the power of 2, whichever one you like, you can use. So I'll use.
Yes, please, sir.
Yes. Let me finish this. Then
Okay, sir.
So p to the power of 2 times p to the power of 3. Again, 2 fingers, one on shift, one on control, and I type enter. Then I have my results. So Adebayo, go ahead, ask your question.
Okay, sir. Sir, thank you, sir, for the lecture so far. This multiplication, I don't really understand what we are multiplying together. Is it that we are raising whatever figure to raise power 2? Like, sir, you are using the old Excel this now. We don't want to use calculator. Please, sir, can you put us through? Because it's somewhat confusing.
No, it's not confusing. You have done matrices before. At 411, I'm not teaching you matrix multiplication. So I'm only using this to hasten my teaching. So you know that you will use your rows to multiply your columns. Abi, add them and then do for each of the cells. So I'm only using the Excel to aid my teaching so that I can cover enough ground in a very short time. So you will have to learn how to, or revise, or try to recollect how you multiply. So let me just show you, just for the sake of showing you. So if you have 2 cells, 2 matrices, let me copy special values. Okay, this one matrix, I'm using it to multiply another matrix V. The procedure is that I will pick this row, okay? I'll use it to multiply, let me paint it yellow. I'll use it to multiply this column, I'll paint it red. Then I'll get my answer. So how do I multiply? I will use this 0.3 to multiply 0.3 here, plus 0.6 will multiply 0.125 here, plus 0 here will multiply 0.428. Whatever I get is just one cell. I will repeat the process. I will use this first row to multiply this first column. Then I will get another cell. I do it again to get the second column. That gives me 3 different values. Then I repeat the same for row 2, against the column 1 and so on. That is what you were taught. That is how it is done. And this is exactly what the Excel is doing. I've just made sure that I could just do it on time. And I was putting a control to it. Deliberately, I was adding to be sure that I'm not making any mistake. My addition, the addition of the rows must be equal to 1. Okay? So, and that's what I was doing and for the calculation. So now let's interpret this result. You will see that from P2 to P5, none of the cell is 0, which means that you are dealing with a regular Markov chain. Regular Markov chain. Okay? And let me paint this red. Now you will see that the probability that a process or a customer that is currently enjoying 10% discount now will continue to enjoy 10% discount by next month, it is 34%. That means 0.34 325 is the probability that a customer that is currently enjoying 20% will be on the same 10% in the next month. So that's how to do the interpretation for each of the probabilities. And if you have to calculate n step, it simply means raising your power p to power of n. So this is 5 step. This is 4 step. This is 3 step. This is 2 step probability. And that is 1 step probability. And what's it about? It's about the probability that your process will transit from one state to another at the given time. So P, 1 step simply means at the end of 1 month. 2 steps means at the end of 2 months. 3 steps means at the end of 3 months up to the end of 5 months, as we have had in our example. So I'll go back to our slide. We are almost done. So you agree with me that this is a very simple concept, very exciting as well. So you have raised your power, you have computed your transition matrix, your transition graph, and so on. So there's some properties that you need to consider. Irreducibility, ergodicity, stationarity, and so on. And then we have different examples similar to what we have done earlier, similar to the example of the customer enjoying discount level and so on. It's the same concept that we have introduced, just trying to make it simpler, how to multiply and all of those. So the last concept I'm going to introduce is the long-run behavior. It's called the limiting distribution of our transition matrix. That means, so you can see that I was multiplying the probability by itself, over a period of time, and the probability were changing and so on. The question now is there a point in future where if you raise your P to it, that future, if you raise your P to that future, the probability will be the same as the previous one. That means it will have reached a stability at that point. And what it means is you'll be able to get the probability of being in any of the states, irrespective of where you are. What's the probability that you are in state 1? What's the probability that you're in state 2? What's the probability that you're in state 3? So it's actually computed using this simple expression, pi equals to pi p. Of course, where the summation pi equals to 1. The pi are the limiting distribution or limiting probability that you are looking for. P is the transition probability that you have been given. So you are looking at that pi, that when you multiply with the pi p, you end up getting pi. So you can solve analytically, and then you get your result. Let me show us how it is done in Excel. I'll keep raising the power. I can do p to the power of 10, p to the power of 20, and let's see whether the a stability will have been attained. Now let's see it. Let's see. I know some of us are fasting. I'll make sure that I release you guys before in the next 5 minutes or so. So now let's do p to the power of 10. Let us see, okay, if stability can be attained. So let me raise g to the power of 10. I tried to prepare some podcasts for you, And I've tried to also do some videos just to simplify it. Please make sure you look at it so that you can have an understanding of it. Okay, so I want to do p to the power of 10. And I'll do p to the power of 20. Okay? So let me delete. From algebra, p to the power of 10, p to the power of 10 can be p to the power of 5 times p to the power of 5. Do you agree? Yeah, someone is raising his hand. Go ahead. Go ahead.
Yes, sir. You mentioned that you have podcasts and videos available. Please, where can we see the video or get the podcast?
There's a class governor that was contacting me, and he said he has given everybody in the faculty. Hello, class governor, are you there? Hello?
Hello, sir.
Yes.
Hello?
I want you to confirm. I want you to confirm
Yes,
that you have shared it with them.
I said all materials you sent. I said the YouTube link. I said the podcast. This is my sent to me, sir. So, yes, sir.
But the video, did you share it with them?
Everything you sent to me, sir.
So, lady, you should try and reach out to him so that you can get maybe your number is not, or you are not on the platform. And what you will do for me, Mr. Class Governor, try and reshare so that everybody gets it. I can see that out of about 1,000 students, can you see only 100 and something actually log on? So you can see maybe I guess some students are genius, so they can just get things being taught. Yes, go ahead. Go ahead.
Sir, actually, there's only one YouTube. There's only one YouTube video you sent.
Only one?
Yes, sir. YouTube video you sent. Yes, sir. So you sent a PDF and one PowerPoint slide, and then it's podcast.
Just go to that channel. You will see them there. Once you click this, you will see all the videos there.
Okay.
So you can see in 10 years' time, look at the behavior. Let's see in 20 years' time. Let's see what happens. P to the power of 20. And then you also share the Zoom link, the recorded class for previous sets. Share that one too, so that they have access to all of these and nobody disadvantaged, please. Or some of you can also WhatsApp me directly. I'll forward it to you. So whichever one you prefer. Now, do you notice that the column, the value on column 1, they are all the same. The values on column 2, they are all the same. The values on column 3, they are all the same. This is the steady state probability that there's a point in time in the future where, irrespective of the previous state, if you multiply it with the same P, you will end up getting that same probability. This is the pi. So pi 1 is 0.28571. Pi 2 is 0.38095. Pi 3 is 0.3333. So this is the steady state probability. What it means is, if I have 1 million customers, I'll use that 1 million to multiply all of these. Let's do it. It means that I know the expected number of customers that should be enjoying no discount? How many should be enjoying 10% discount? How many will be enjoying 30% discount? Let me just do it. Sorry. So this will be equal to this times 1 million. So you will see that I expect 285,000, okay, to be enjoying the no discount. And I expect 333,333 to be enjoying 30% discount. This is my expectation. This is my projection. And this is the essence of the Markov chain. So I hope I've been able to make some sense. So do you guys have questions? Let me save this and attach. Can I ask your question? Yes, go ahead.
So just to be sure, so will you be saying the recording and the for this one, like for this class?
You mean
you can go back.
The recording
Yeah,
of
for
this?
this.
Yes. I'll share it. Once it drops, it's being recorded on the cloud. So once it drops, I'll just share it.
Okay, fine.
But
it's yours.
Yes, I'm already doing that now. I will share the Excel immediately.
Okay, fine. Okay.
So on that
End of
note,
the lecture.
I want to wish you guys the best. So, but if you need me, maybe to just do a review, if I have the time, I will. So I wish you the best. Bye-bye for now.
Thank you, sir.
Thank you, sir.